All right, so we'll finish up chapter 6 today. So the last section we're going to look at is 6.5, part 2. And we're going to use the trig functions that we did in the last section yesterday to solve triangles. So when we're solving a triangle, that just means to find out how big everything is. There's 6 things you have to find. 3 sides, 3 angles. But out of those 6 things, first of all, we're always going to be solving right triangles. So that means every single problem is going to have an angle that's how big? Robin?
90 degrees.
90. So there's 1 out of 6 things that's going to be the same in every problem. Because that's the same in every problem, it doesn't really help you do anything, right? Other than the fact it tells you you have a right triangle. What we need is some other information to help us solve the triangle. There's two different cases of information they could give you. In addition to the right angle, they could either give you the other angle and a side, and that's enough information to find everything, or they could just give you both sides and none of the angles. But that's it. That's the only 2 situations that could ever come up. When we get to the 2-side case, that's where we're going to have to use inverse trig and probably Pythagorean theorem. When we do this case, we're not going to have to use inverse trig. Right? That we can just use regular trig. Okay? But we're going to go through one of each. So a couple things that are going to help us to solve triangles. Facts you already know, hopefully just from geometry. All the angles in a triangle add up to 180. And we can use the Pythagorean theorem, right? Because we are working with a right triangle. Eventually, we're going to do the same thing again. We're going to solve triangles, but we're going to do it when you don't have a 90. When you don't have a 90, it's a little different. You can't use Pythagorean theorem. Right? As long as we have a 90, which we will today, you can use it. All right. So whenever we do this, we're going to use one of 3 trig functions. We're not going to use the secant, the cosecant, or the cotangent to do any of this. You could, but the reason we stick with these 3 is because your calculator has buttons for them. All right. So your 3 choices for trig functions are always going to be sine, cosine, or tangent. And you have to pick the one that works in your problem. How do you know which one works? Well, they're going to give you some information. Depending on what the information is they give you, maybe you're going to know the opposite, and you want to know the hypotenuse. So you have to look for a trig function that has opposite and hypotenuse. Or maybe they give you the opposite, and you want adjacent. So opposite and adjacent are the 2 sides that are involved. So you'd look for a different trig function. So you just have to find the one that matches up with the side that you know and the side that you want to know. That's pretty much it for that. So let's look at this one. So sometimes they'll do a sketch. Sometimes they'll actually just write out a description of the problem. This one, it's just a description. So it says 1 angle in a right triangle is 37 degrees, and the hypotenuse is 8. And the directions are to solve. So that means find the other angles, find the other sides. So there's different ways, once you start finding out pieces of information, there's different ways you can kind of go through the problem. We're going to try to go through it in a way that if we get something wrong, it doesn't mess up other things. So we want to avoid, if we make an error, it messing up everything else. Right? And we can do that. So that's how I'll show you. All right. Especially to kind of get a better sense of like what's opposite and what's adjacent, what might it be helpful to do with all this writing that would make it easier to kind of see what's happening? Yeah.
Sketch a picture.
Yeah, let's just sketch a picture. Doesn't matter how you sketch it as long as you make the hypotenuse 8. And it says one of the angles is 37. Doesn't matter which one. Now, just to give names to the other things we don't know, we'll use letters. For the sides, what are the letters we always use? Rob?
Is it the one that looks like a fish? Alpha, is it? Or is it?
We're going to use those in a minute, but not for sides.
Oh. talking about letters?
That is a letter. It's just a Greek letter. We're not going to use Greek letters yet.
A, B, and C.
We're going to use English letters for the sides. So A, B, and we'll just call that one C. And now we'll use Greek letters to represent the angles we don't know. Does anyone remember the Greek letter we always put across from A?
Yeah.
Which one?
Alpha.
Alpha. And even though we already know it, the Greek letter we put across from B is beta. So what I'm going to do now is I'm just going to make a table. And I'm going to write down everything I know, everything that I need to find. So I'm going to put 3 sides in one column, and then the 3 angles in the other column. For now, we don't have to label the angle across from C because it's always 90. When it's not, we'll give it another name. We'll use another Greek letter. All right, and let's see. So beta, if you want, just so I can be clear, I'll put it inside. So beta is 37. Let's see, what else do we know? C is 8. And I'm going to put boxes around the 3 things we don't know. A, B, and alpha. Okay. So those are the 3 things we have to find. Now the way I'm going to show you to do it, you can do it in any order. But there is one thing there that I think is faster to find than maybe other things.
You would minus 37 from 90.
Yeah, if you just do 90 minus 37, because all the angles have to add up to 180, tells you that alpha is 53. Okay. Any question on that one? Now, to find A and B, you have a choice. You can use either the 53 and view everything from that perspective, or you can do it from the perspective of the 37. If done correctly, you get the same answer both ways. But which one do you think is a better choice to use, like a safer choice? Yeah.
The 37.
Why?
Because you already know that one's right because they gave it to me.
Yeah. So we know the 37 is right because they gave it to me. If I use the 53 and I made a mistake, then everything I use it for is going to come out wrong. Right. So let's stick with the 37. So we're going to circle, we're going to use that. And now we have to pick 2 sides because a trig function always involves 2 sides, either opposite and adjacent, opposite and hypotenuse, or adjacent and hypotenuse. Well, it's got to involve hypotenuse because that was given. Now I've got a choice. I can do A or I can do B. Gabe, which side do you want to try to find first, A or B? I'm going to do A. So now what we have to figure out is what trig function to use here. To do that, just figure out the names of the 2 sides. So Ashley, what's the name of the side that's across from the hypotenuse? It's 8 units long, but it's, I actually think I just told you. It's the hypotenuse. So let's do a different question. The side that we've labeled A, it's right next to the 37. And what do we call that side?
Adjacent.
Adjacent. So we're looking for a trig function that has adjacent and hypotenuse. And out of sine, cosine, and tangent, only one of them does. Okay? Cosine. Okay, so let's set this equation up. So we're going to do the cosine, and it's always the cosine of your angle. Okay, that's your argument. That's the thing you're taking the cosine of. So you're going to take the cosine of 37, and that's equal to adjacent over hypotenuse. Nate, what's adjacent here?
Adjacent would be A, right?
Yep, and hypotenuse?
C through 8.
Is 8. So A over 8, and now just solve that for A. So how do we get A by itself there? Yeah.
Multiply both sides by 8.
Yep, multiply by 8, multiply by 8. And we need to type that in to get a decimal. But once we do that, that is the answer. 8 cosine 37 degrees. All right, so on my calculator, if I type it in right now, I'm going to get it wrong. What do I have to double check? We've got to check this a lot, right?
Change it to degrees.
Yeah, these are going to be all in degrees. So just put it in degrees. And now you're okay. 8 cosine 37. So side A is 6.389. Okay, we'll go to 3 decimals. 3.389. Now, I've got 2 out of 3 of the sides in the triangle. So what could I use now to get B? Yeah?
A squared plus B squared equals C squared.
Yeah, I could use the Pythagorean theorem to get B. But in this case, there's a couple reasons why I don't want to do that.
Decimal.
One reason is it's a decimal. That's not an exact answer. It's rounded. So if I use something that's rounded, B is going to be even less accurate. What's another reason why I might not want to do it? Yep.
You could have made a mistake, so there's more of a chance for error.
Yeah, it might not even be right. Maybe the answer is 5.6. Maybe it's not 6.3. So if we made a mistake, then we use it, we're going to get B wrong. So now that we have A, we're going to forget about it. We're not going to use it. We're going to go back to the 37, because that's what we were given. We were given the 8. And now this time I want to find B. So now focus on what's circled in red. Figure out the names of these 2 sides. And then from there, we'll pick either sine, cosine, or tangent. Well, it's not cosine. I already did that one.
Fine.
Yep, sine is opposite over hypotenuse. So let's find C. So we're going to take the sine of, and Kaya, what's my angle?
37 degrees.
Yep, 37 degrees.
Would it be fine B?
What are we finding? Oh yeah, B, thank you. Never happened. Find B. And what's going to be the fraction on the other side? What over what? Yeah.
B over 8.
B over 8. So we've got B over 8, and it's pretty much the same pattern as last time. Just multiply by 8. Okay. Now we'll see what that comes out to. Now, I know that B is across from the smallest angle, so it has to be the smallest side. Okay? So it's got to be smaller than 6.389. But it can't be too small, because if you add any 2 sides together, they have to be bigger than the third. So for example, B couldn't be 1, because if I added 6.3 to 1, it's not bigger than 8. So any 2 sides added together have to be bigger than the third, and it has to be the smallest side. So I guess it's around, maybe, could be like 3, 4, somewhere around there. Let's see what it comes out to. 8 sine 37. Right, so 4.815. And that's always true in any triangle. The biggest side should always go with the biggest angle. The smallest side with the smallest angle. And any 2 sides added together have to be bigger than the third. If any of what I said is not true, then something's wrong. But that looks pretty good. Now, if you had extra time, you could use Pythagorean theorem now to check it. See if a squared plus b squared equals c squared. So a squared plus b squared should be about 64. And if it is, that's a good way to check it. Okay. Any questions on that one? So no inverse trig at all, because all we had to do was find sides. Finding the angles, we didn't really have to calculate. We just had to subtract from 90. I mean, I guess that's a calculation, but it's a very, very simple one. Nothing fancy. Does anyone want to see another one where you're finding a side and an angle? Like the one we just did? No. The only extra step here is you would have to draw it first, and I would draw it this way. Put A across from alpha. It's the only thing you have to remember to do. A across from alpha. And now you can label the rest and solve. Right? I would get the angle. Oops. Mess that up. I would get the angle first, because you could just subtract 20, get the angle as 70, and then use the 20 though to figure out everything else. Don't use the 70. Okay, let's look at this one. So this time they're giving us the hypotenuse and one of the other legs. They're not giving us any angles. So this will be a little different. And just like I did on the first problem, and I kind of started to do on the other one, what do you think I should do with all that information first? No?
Draw it out.
Yeah, let's draw it out. I mean, some people can just kind of see in their head what's opposite and adjacent. They don't need a picture. But it doesn't hurt just to make a picture. So they tell me that the hypotenuse and one leg of a right triangle are 12.7 and 6.1. Which one of those must be the hypotenuse? Blake? Yeah, even if it didn't say respectively, which means in the order it was written, that's what they're giving you. How do you know 12.7 has got to be the hypotenuse?
It's the largest one.
Yeah, if you give me two numbers and one of them's a hypotenuse, it's got to be the biggest one. All right, so 12.7. And it says one of the legs. Doesn't matter which one. If you put the 6.1 in a different spot, then you're going to get the same two angles I get, just switched. All right. So now, what can't I do first that I was able to do in the first problem right away? Like I was able to do a simple calculation to get something quick.
You can't find the angle.
I can't find the other angle because I'm missing both. So I don't have anything to subtract from 180. But there is something I can do this time, and I'm okay with it, but I wasn't okay with it last time. Yep.
Pythagorean theorem.
Yeah, why am I okay with it this time?
Because they gave you two sides.
Yeah, because I'm going to plug into it, and everything that I plug into it is given. So that's okay. So we should probably label, let's call this A, B, and C. And it's going to be alpha and beta. What you really call the sides and angles is not really important. I mean, it's just there for you to kind of help you make sense of what's going on. But if you want to call them something and do it, that's the way to do it. All right. So let's set up our equation for Pythagorean theorem. Joe, could you set that up for me?
So we do.
Yeah, you, Joe.
So 6.1 squared plus b squared equals 12.7 squared
6.1 squared, yep.
plus b squared.
Okay, yep. And then what's that equal to?
12.7 squared.
Yep, perfect. Okay, so as we go through, we'll have to round this a little bit, but we're going to stick with three decimal places if it goes out that far, which this one won't. 37.21 plus b squared. How about 12.7 squared? Does anyone have that?
161.29.
161.29. All right, so now from that, can someone subtract 37.21? Just do. Yep. 124.08. And then the last step, and at this point I'm going to put approximate because now we're actually going to round. We didn't do any rounding up to that point. The square root of 124.08. Just a little more than 11. What does that come out to? Yeah, Joe.
11.139.
11.139. Right. So any questions on our first side? All right. So let's make our table just so we've got everything in it. B is 11.139. Put a box around it so I remember that that's something I found. And alpha we don't know. And beta we don't know. I'm not going to write the right angle because it's always the right angle in every problem we did this week. All right, so to find alpha and beta, I have to use two sides. Justin, what out of the three that I know, which two should I stick with?
For what?
Which two sides should I stick with? Well, I've got to use two sides.
A and C.
Why A and C? Why not B?
Because it's a little wacky.
It's wacky? All right, it could be a little wacky.
And
What makes it
A and C are
wacky?
Given to
It wasn't given, yeah. So it's a decimal and it wasn't given, so we're going to kind of stay away from that side. So we're going to stick with A and C. And now at this point, we can pick either alpha or beta. Let's do beta. So we're going to find beta. From the perspective of beta, what two sides are circled? It's like opposite and hypotenuse, or adjacent and hypotenuse, or opposite and adjacent. Yep. Yep, it's adjacent and hypotenuse. And out of the sine, cosine, and tangent, which trig function has those two? Cosine. So let's set up our equation. Cosine of my angle. What's my angle? Beta. I don't know it. So cosine beta equals adjacent over hypotenuse. 6.1 over 12.7. Now, if we compare that equation to something like what we had here, what's the difference? They're not the same type of equation. They're a little different. So we had that, and now we have that. Yep.
Variables in a different spot.
The variable is in a different spot. The variable is inside the cosine function. It's kind of like if you had something like this. The square root of x equals 10. Well, the variable is inside another function. So if I had the square root of x equals 10, I cannot use adding, subtracting, multiplying, dividing to solve that. The problem is you've got a function right here that you don't want. So you've got to get rid of that function with another function. It's opposite, or it's inverse. So for square root, the inverse function is what? Yeah, squaring. Okay, squaring cancels out a square root. Well, we've got the same thing here. We've got a function right there that we don't want. You can't add, subtract, multiply, or divide by a word or a function. The only way to get rid of it is another function that would cancel it out. And that's what we have at this step. So we need to cancel out cosine, and we're going to do this with inverse trig. So I'm just going to explain what that is quickly, and then we'll actually go back and do this. So you might want to leave a little room to do some work, because we got a little more work to do. Or you could just do it down below, whatever you want. Okay. Now we're going to look at inverse trig. So those things you saw in the calculator with the little negative ones, like above the trig function, that's what we're looking at. So there's two ways to write inverse trig functions. The way on the left is what you usually see on your calculator. If you press second sine, second cosine, or second tangent, there's the three inverse trig functions. Another way to write them is what I have next to them. Arc sine, arc cosine, or arc tangent. They mean exactly the same thing. I usually stick with the way on the left. But if you're taking a test or get something and it says arc sine and you don't like it, you can cross it out and just write this symbol instead. It means the same thing. And there is inverse secant, inverse cosecant, and inverse cotangent. Again, there is no button for it, but you can still do it on the calculator by using the buttons that you do have. We'll see. I'm not sure if we get into that today or not. Okay, so let me just show you an example of something with inverse. Let's do the inverse sine of the sine of 30 degrees. When I hit enter, what do you think I'm going to get? Yeah?
30.
30? You sure?
Yeah, because I cancel, right?
Yeah, because they cancel out. So the sine, inverse sine and regular sine cancel each other out. It's just like doing the square root of 30 squared. Well, you just did something to the 30 that, and then you're going to undo it right away. That's what square and square root do. So you get the same answer you started with. How about if I did like the inverse sine of the sine of 75? If I hit enter, what would I get there? Yeah. Yeah, 75. So if I hit enter, inverse sine and regular sine cancel each other out. How about the inverse sine of the sine of 210? What do you think I would get? Yes, yeah? You might guess you get 210, you don't. We're not going to talk about that one right now. We would never be dealing with an angle this big in a triangle anyway. Turns out that this little formula only works if your angle is up to 90 degrees, but that's not an issue because we're dealing with right triangles. The angle would never be bigger than 90. So later on, I'll show you why this happens, but not yet. Okay, so for our purposes, basically you can just think you got a regular trig function next to an inverse. They cancel each other out. So let's see how we can solve this one. All right. So I want to get rid of cosine. So I'm going to take the inverse cosine of each side. But you're not multiplying. You can only multiply with numbers and letters. You cannot multiply with a function name. Okay? Just like you can't take like 6 and say multiply by the square root. You can't do that. Or like take 6 and multiply by a parenthesis. You know, this is something you can't do, right? So we're not multiplying, we're taking the inverse cosine. So take everything that's on the left, and that's going to get plugged into the inverse cosine. Take everything that's on the right, and that's also going to get plugged into inverse cosine. So on the left, what's going to happen with inverse cosine and regular cosine? Yeah?
They're gonna cancel.
They're going to cancel out. Now, do they always cancel out? No. This only actually works if this number is between 0 and 180. But I guarantee you this number is between 0 and 180 because it's an acute angle in a right triangle. In fact, I can do better. I can say it's between 0 and 90. So I know this trick is going to work. So now those are gone. I get beta by itself on the left, and now I need to do what's on the right. It's inverse cosine, and the argument you're plugging in, 6.1 over 12.7. Even if that reduced, I wouldn't worry about it. Just leave it like that. Okay. Inverse cosine of 6.1 over 12.7. I get 61.294. And what is that? 61.294 represents what in this problem? What did I just find? I found an angle, and that's the key. Anytime you do inverse trig, you press an inverse trig function and you hit enter, the number you get on the screen is an angle. That's when you use inverse trig, when you need to find an angle. All right, so 61.294. Okay, so there's beta. Now, I could subtract that from 90 to get alpha, but we've already talked about why that's not a good idea. All right, so let's do alpha the same way we did beta. Go back to my picture. Again, you don't need to circle these in different colors. I'm just doing it so you can see it. But I'm going to stick with the two sides that were given. And this time I want to find alpha. So now switch your perspective. Looking at everything from alpha, what are the names of the two sides that you are given? Okay?
Opposite and hypotenuse.
Opposite and hypotenuse. And what trig function is that?
Sine.
Sine. Okay, so we're going to write down sine of my angle, which in this case is alpha, equals, and Nate, what's going to go on the other side? of the equation. Sine of alpha equals,
Sine of alpha. 6.1 over 12.
yes, 6.1 over 12.7. Okay, so now we got an equation. We got to get alpha by itself. It's inside the sine function, so we got to get rid of the sine function. Tori, how do I get rid of my sine function?
You use the inverse of sine.
Yep, we're going to take the inverse sine of everything on the left and then everything on the right. So I'm just going to squeeze it in here. Inverse sine, regular sine, cancels out. Take the inverse sine of everything that's on the right. And once we type that in, that's our answer. So let's see what we got. So inverse sine of, and then it's the same, it's actually the same fraction. 6.1 over 12.7. Okay, so we get 28.706. Now, a quick thing we could do to double check is add those up. And what should alpha and beta always add up to? Should always add up to 90. And we found them totally separate. We didn't use one to find the other. So that's a good, good way to check. So 0.706, 61.294. And now this time they do add up to exactly 90. But you might get like 89.999, okay, because of rounding. Okay, so any questions on that? All right, so you only have to use inverse trig if you're trying to find an angle. That's the only time you use it. Otherwise, if you're trying to find a side, you use regular trig. Or you can use Pythagorean theorem if everything is given. All right, so we went through that. This is another one with two sides. So it's just like this one. In fact, it's almost the same thing. They're giving you a hypotenuse and a leg. So any questions on how you'd solve this one with two sides again? Would you use inverse trig here or no? You think, Madison? What do you think?
Yes.
Why?
Because they only give you sides.
Yep, they only give you sides. You got to use inverse trig. Is Pythagorean theorem okay?
Yes.
Yeah, everything's given, so that's okay to use too. All right, so let's look at something that's going to kind of tie in a little with what we did yesterday. So when we do trig, does it matter what size triangle you use? Like if you have a 30, 60, 90, and I draw a bigger 30, 60, 90, and we both use it to find, say, the cosine of 60. Are you going to get a different answer than me because I got a bigger triangle and yours is smaller? No. The size of the triangle doesn't matter. Certain size triangles are easier to work with than others. Okay? Obviously, like if you got a 1 in there for a side, that's an easy number to work with. But let's take a look at this. Okay, so what I've drawn here is two circles, okay, one inside the other. And the smaller circle, that's a unit circle. If we have a unit circle, what does that mean the radius is? It's 1. Okay, so then that smaller circle is a radius of 1. That bigger circle is a radius of r. It's unknown. It's bigger. Technically, it could be smaller. This trick works both ways. But let's just draw a line in going right through that point to the edge of the bigger circle. All right. So, and I'm going to also make this into a triangle by drawing a perpendicular straight down from there. So when we want to do unit circle trig, the goal is to work with a triangle that size because the radius is 1. But let's say they gave us a point way out here. That's a little harder. Okay? It's on a bigger triangle. It's on a triangle this big. And that radius is r. So if you look at those two triangles, though, there's a word we can use to describe them. They're not congruent, but they're similar, right? They basically have all the angles in common. They each have a 90, and they share this angle right at the origin. So they are similar triangles. So if we can turn the bigger one into the smaller one, maybe by shrinking it down, we can do what we already know how to do with unit circle trig. It's just a matter of shrinking down that bigger triangle. So now let's say the coordinates of this, just move that out there, is x and y. So that means this side is x and the height is y. X and y. My goal is to scale down the triangle on the left. I'm sorry, scale down the triangle on the right to make it the same size as the one on the left. And if I can do that, I can use all the formulas that we already learned for unit circle trig. So what we'll do quick is just kind of go through what those formulas were. Unless I already, yeah, I have them right here. Does anybody remember what the sine was equal to? It was just a single letter in the coordinate. Yep.
Y.
Yep, sine is equal to the y value of the coordinate. How about cosine? Yep.
X.
Yep, cosine was x. And how about tangent? That one was a fraction.
Y over
It was y over x. Now, when you look at that at first, you might be like, well, we're doing opposite and adjacent this week. How are these really related? It's exactly the same thing. Opposite over hypotenuse, adjacent over hypotenuse. Look back up at your triangle. Look at this small triangle right here. If I labeled those sides 1, x, and y, pretend that the bigger triangle doesn't exist, and I view everything from the perspective of where that blue arrow is pointing. Sine is opposite over hypotenuse. Well, opposite is y, hypotenuse is 1. Y over 1 is just y. Okay. Viewing again from the perspective of where that arrow is pointing, cosine is adjacent over hypotenuse. Adjacent is x over 1. Cosine is just x. Tangent is opposite over adjacent. Opposite is y, adjacent is x. So these definitions are exactly the same thing as opposite over hypotenuse and adjacent over hypotenuse. And then we flip them all. Okay, so that's what we did on the unit circle. Those 6 formulas only apply to the small triangle because the hypotenuse is a 1. We can make them apply to a bigger triangle as long as we can turn the bigger one into the smaller one by scaling it. And you have to scale it down so that the hypotenuse is 1. That's all you have to do. So if I had a triangle that was had a hypotenuse 6 units long, what could you multiply 6 by to make it a 1? Could you scale the number 6 down by to make it a 1?
1/6.
1/6. What if I had a hypotenuse that was 8 units long? What could I scale the number 8 by to make it 1 unit? 1/8. Now, what if I had a hypotenuse that was r units long? What could I scale down r by to make it exactly 1? Yep. 1 over r. And if you scale this side by 1 over r, and you want to keep the triangles similar, what do you have to do to the other sides? Yep.
Also scaled by 1 over.
Right, basically dividing every side by r. So r, we scale it by 1 over r, that side turns into 1. When we take x and scale it by 1 over r, that turns into x over r. And we take y, and we scale that side by 1 over r, and it turns into y over r. So kind of the important thing here is r turns into 1, x turns into x over r, y turns into y over r. So all you have to do in these formulas is everywhere you had an x, you're going to scale it by 1 over r. and make it x over r. Everywhere you had a y is scaled by 1 over r, and it becomes y over r. So I'm gonna write those out. So sine was y. You're scaling y by 1 over r. It turns into y over r. All right. Cosine was x. Well, x is now scaled by 1 over r. So it becomes x over r. That's your cosine. And the tangent was y divided by x. Well, that's y over r divided by x over r. That's what it would become now. But if you look at that, when I do y over x, changing them by scaling by 1 over r, what happens when you divide those out? Yeah.
The r's cancel.
The r's cancel, and you end up with exactly the same thing you had before. So tangent ends up staying exactly the same, y over x. And now, once we have these three, to get the next three, what would we do with them? Yeah, we just flip them. So your cosecant is r over y. Your secant is r over x. And your cotangent is x over y. It's exactly the same thing we said yesterday. If you just think of it like this. Yeah, x, y, and r, and put your perspective right there. Sine is opposite over hypotenuse, y over r. Cosine is adjacent over hypotenuse, x over r. Tangent is opposite over adjacent, y over x. There's no difference between this and what we did yesterday. We're just giving them different names. Okay. Now, if you change all the r's to 1, okay, don't write this, but if you did, make all your r's 1s. Look what you get back. Y over 1, x over 1, 1 over y, 1 over x. Those are the original formulas. So these formulas are really a special case of these formulas. It's just I let all the r's be 1, okay, to make it easier at first. I lost them, wherever they are. Okay. But those are our 6 trig functions on a circle that has any radius you want. So there's one extra step you got to find. You have to find the radius. They'll always give you the x and the y, and you have to find the r. Okay, so let's try one. So they want us to find the 6 trig functions for the coordinate 2, 3. Now they're not telling us what the angle is. All they're telling us is if you make a circle and you draw a point from the origin to 2, 3, that's what the angle would look like. All right, so if I do that, let's take bigger. It's going to write away. I don't have enough space, but that's okay. All right, so the point 2, 3 is on the terminal side of the angle. 2, 3. So if you want to visualize it kind of as a circle, what they're saying is this. There's your circle. I don't know how big that circle is. I don't know its radius, but I need to figure it out. There's the angle they're talking about in the problem. Right here. This side is 2. Do it in a different color. This side is 3. They want us to find all the trig functions of that angle. All right, so finding, in order to use these definitions, we need to know the radius. But finding the radius is really just like finding the what in that triangle? Emily? Yeah, it's just finding the hypotenuse. So your first step is to find the hypotenuse using Pythagorean theorem. And what is the hypotenuse, or what does the radius come out through there? Just as like just the square root of what number?
13.
Yeah, it's the square root of 13. So we'll just go with that. All the rules with square roots still apply. Don't leave it in the bottom. If you can simplify it, do that the best you can. So now sine, y over r. Oh, there's y. There's r. And that's the sine. If you want to think of it as opposite over hypotenuse, it's the same thing. But we're kind of trying to think of it as a coordinate representing a point on the edge of a circle. How about my cosine? What would be the cosine? Well, Charlie?
The cosine would be 2 over the square root of 13.
Yep. Yeah, we'll come back and fix those in a second. I just want to get through them. And then the tangent is just 3 over 2, which means the cotangent, we can do that one pretty quick. Ryan, what would the cotangent be?
2 over 3.
Yeah, 2 over 3. And Natalie, can you fix, it doesn't matter, we'll fix the top one for me.
3 root 13 over 13.
Yeah, 3 root 13 over 13, and this is 2 root 13 over 13. Now, I left them with the original and the fixed version because it's easier to flip the original when we do cosecant and secant. Then your root goes to the top, and you're done. So secant root 13 over 3. And that was cosecant, and now secant root 13 over 2. Which corresponds to r over x and r over y for those two. Okay, so any questions on that idea? Like if you get a coordinate, how to find the 6 trig functions of that coordinate. Just think of it as sides of a triangle. That's all it really is. All right. So now what I want to do is I want to actually figure out the angle. We found out a bunch of stuff. We've got the sine, we've got the cosine, we've got the tangent, but we still don't know how big that angle is. So my goal is I want to get theta by itself. What do we have to use anytime you're trying to solve for an angle? Yeah?
Inverse trig.
We have to use inverse trig. And technically, I can take any one of these 6 and do inverse trig. If you knew how to type in the 3 on the right. We haven't done that yet. But let's stick with one of the ones on the left, and let's stick with the first one. The sine of theta equals 3 over square root 13. Or you could do cosine. It doesn't matter. I'll do both, and I'll show you. So what was it? 3 over square root 13. Now, I'm okay with you using the square root in the bottom there because that's not a final answer. That's just something we're going to plug into a calculator to get a final answer. Right? As long as you don't leave it as the final, for me, it's just easier to type that in. Right, so Kathleen, how would I get theta by itself and get rid of sine? Yeah. I'm going to take the inverse sine and just kind of squeezing it in, the inverse sine. So theta is the inverse sine of 3 over square root 13. Let's see what we got. 3 over square root 13. Okay, so we get an angle of 56 point, rounds up to 3.1. 56.31. Now, if you said, could I have used the cosine? Yeah, I already said you could do that. If you take the inverse cosine of 2 over the square root of 13, watch what you got. 2 divided by square root, square root 13 you get exactly the same thing. So doesn't matter if you use inverse sine or inverse cosine. We're going to kind of stick with a pattern for doing it, and I'll show you in a second. But any of these will give you the correct answer. Any questions on how we got that angle? Now what we have to be careful about is if we didn't know the coordinates of that angle, I wouldn't know the quadrant it's in. And that's when you can end up getting multiple answers. Okay? A lot of times there's two answers. So I'm going to kind of show you what happens with that right now. So 2, 3 is in the first quadrant. So I know the answer is supposed to be acute. Because the first quadrant contains all the angles between 0 and 90. But what if it was in quadrants 2, 3, and 4? Well, there's a formula for how to find theta in each of those quadrants. And the first step is to do what we just did. If you have a coordinate that has a negative in it, you're automatically in quadrants 2, 3, or 4. So step 1 is to find the absolute value of the inverse sine. You always want to use inverse sine. You can use other functions, but if you do, these directions won't make sense. So this is one way to do it. And when you find the absolute value of inverse sine, this is called a reference angle. It's a reference angle because it's not the final answer. It's something that we're going to reference in a formula to get the final answer. Okay, we'll do an example, but let me just give you the formulas first. If you know that you're supposed to be finding an answer in the second quadrant, and you know your reference angle, you do 180 minus your reference angle. Now your reference angle is always going to be between 0 and 90, always. It'll never be bigger than 90. It'll never be smaller than 0 because you're taking the absolute value. So it won't be negative. Right? So if I give you a coordinate and I ask you to find the angle represented by that coordinate, and you know you're supposed to be in quadrant 3, and you know you're in quadrant 3 because the coordinate would have a negative in it. That's quadrant 3. You take your reference angle and add 180. Then if you're looking for an angle and the coordinate I give you is in quadrant 4, it's 360 minus your reference angle. We use these formulas a lot in chapter 7. So quadrant 1 is the easiest. You don't have to do anything at all. Just take the inverse sine of your angle. This is how you do quadrants 2, 3, and 4. And because I put out a little sloppy here, but the 180s and the 360s, what units do you think those are in? Those are all degrees, yeah. If you want to do it in radians, pi minus your reference, pi plus your reference, 2 pi minus your reference, if you're doing it in radians. Okay, so let's find the angle represented by the point 2, -3. It's got a negative in it, so we're not in quadrant 1. We've got to figure out our quadrant. All right, let me, you don't have to draw a picture, but I'm going to draw one this time just to kind of show you what they're looking for. 2, -3. That's on the terminal side of an angle. All right, so if you wanted to make your circle, there's a circle. Here is the initial side of my angle. Here is the terminal side. That's what I'm trying to figure out. How big is that arc, okay, that angle? So what I'm really going to be doing is, well, what quadrant is this point in? It's in the 4th quadrant. So what I'm really going to be doing is I'm going to find a reference angle and subtract it from 360. I'm going to find what that little piece is, and I'm going to subtract it from 360, because 360 is all the way around. If you take out that little piece, that's what we want to know. How much is it to go all the way around except for that little piece? So that's why it's 360 minus. Once you do some problems, the formulas kind of make sense. All right. So it says find my reference angle. How do I do that? The absolute value of the inverse sine. Okay. So I make my triangle. I'll do it in a different color. That's 2, and that's 3. Let's write it because we're going to need it. What's the hypotenuse there? The square root of 13. Yep. So my angle equals the inverse sine. And now we just need to figure out the formula for inverse sine, but we just did that. Inverse sine is y over r. All right, so let's look at it. Look at your coordinate. There's y, so it's -3 over, and we had to calculate the r using the Pythagorean theorem. That's the square root of 13. Okay, so do that out, and whatever you get, just make sure you take the absolute value of it, and that's your reference angle. So inverse sine of -3 over square root 13. It's not really critical you close parentheses because you're not typing anything else after it, but if you want to. Just don't accidentally hit 2 parentheses. Okay, so I get an angle of -56.31. So what's my reference angle in this problem? Yep.
56.31.
Yeah, 56.31. So this little section that I just colored in green is 56.31. So what do I subtract that from to find the section in red? Yeah.
360.
Subtract it from 360. So find theta. So in this case, theta equals, and now I'll just subtract it. 56.31 subtracted from 360. So that big angle in red is 303.69. And that's the answer. Question on it? It's a little bit of work to remember which formula to use, but a lot of times if you just draw it out, you can almost make sense of it without even thinking of these formulas. Okay. All right, so the quadrantal angles are kind of a special case. If they ask you to find the trig functions for one of those, you're only going to get one of 4 answers. A 1, a -1, a 0, or undefined. And that's because every one of those angles is on an axis. If you have a point that's on an axis, the coordinate would always have what number in it? Yeah?
0.
A 0. So every one of these points is 0, comma something, or something, comma 0. Do I have an example? Or? So let's just say they asked you to find the sine of 90 degrees. First of all, does it matter how big of a 90-degree angle you make?
No.
No, they're all similar. So in terms of thinking of it on a circle, if you said, well, where should I put a point for 90 degrees? You can put it anywhere on the positive y-axis. Here, 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 here. It doesn't matter. Okay? You can put it anywhere there. Let's say you put it right there. Right? And let's say that that coordinate is 0, 4. Well, if I wanted to find the sine of 90, I need three things. X, Y, and R. Well, I already have X and Y. That's 0 and 4. What's R? I don't really have a triangle here because my point is right on the axis. So what would R come out to? You can find R the same way we did before. Just do x squared plus y squared equals r squared. You're really just doing, just do the Pythagorean theorem. X squared plus y squared equals r squared. We did it with a 2 and a 3, and we got the square root of 13. What do you get if you do it with a 0 and a 4? How much?
4.
Yeah, you just get 4. So it's kind of even pointless to write it, but if you want to write it, you can. And now the sine is y over r. 4 over 4, which comes out to 1. The cosine would be x over r. 0 over 4, which comes out to 0. The tangent is, let's see, tangent is y over x. 4 divided by 0. When you divide by 0, what do you get? Undefined. Yep. So it wouldn't have mattered if you said, well, what if I called this 0, 5? It doesn't matter. It's just a bigger circle. It's all similar. Okay? These would both be 5s, and you'd get all the same answers. All right. Maybe you want to use 1. You know, think of a unit circle. That might be the easiest way to do it. All right, so last thing I'll give you is a diagram that shows you where certain trig functions are positive and where they're negative. This diagram combined with these formulas right here, we use a lot in chapter 7. So I'll give you the diagram and then I'll kind of explain it. The letters stand for the names of trig functions. S stands for sine, T stands for tangent, C stands for cosine, A stands for all. In quadrant 1, all the trig functions are positive, meaning you can give me any angle you want between 0 and 90. I can take the sine of it, the cosine of it, or the tangent of it. It will always come out positive. If you give me an angle in quadrant 2 between 90 and 180, the only answers that will come out positive are the sines. So if you said, is the sine of 120 degrees positive or negative? I'd say positive. No, it's positive. How about the tangent of 120? It's negative. In quadrant 3, any angle in quadrant 3, your tangents come out positive. Any angle in quadrant 4, only the cosines come out positive. I already kind of wrote that. Okay, so it's just a diagram telling you where the trig functions are positive. And obviously it tells you where they're negative too. You know, if you know tangent is positive in quadrant 3, everything else is negative, meaning sine and cosine. Okay. Any questions on that diagram? All right, so we're going to do more with that diagram in chapter 7. Okay, so homework for tonight is same page. Actually, it's one page later than last night, I think. It's 25 to 34. 40 to 42, 45, and then 49 to 53 odd, and 57 and 61. Okay, so just a reminder, I will be after school today, so if you need anything, I'll be here. Anything you need to make up. No test this week, and your last homework assignment for the term is on Friday.